All right, well, I apologize if the lapel mic picks up on the sound of my stomach rumbling. So yeah, thanks for the introduction, Heather. I'll be telling you about my attempts to model and understand granulation at the spectral level using empirical observations of the sun. But before I get into that, I do want to advertise I also have a poster on other science using SDO HMI observations to understand and probe center to limb velocity variations in different solar regions. So as we've seen in the previous talks, granulation, so turbulent convection at the surface of the sun, produces a number of effects in our spectra. We have the broadening of lines that you may have heard referred to as macroturbulence. This granulation also introduces an asymmetry in lines. I'll talk about this much more. And then as we saw before, we also have this absolute convective blue shift, where the blue shift of the center of your line is correlated with the depth of that line. As we have seen a little bit, the anatomy of a granule, if we take a slice of the surface of the sun, we can see that we have blue shifted light coming from our granule that is brighter than the red shifted light coming from our intergranular lane. And of course, when we look at stars or even at the sun, we often don't resolve these. So what we get instead is an asymmetric line profile with a bisector, where the bisector is tracing the physics and the velocity fields over the formation height of your line in the solar atmosphere. And of course, if we look at these in real data, for solar type stars and disk integrated light, we see these classical C shapes. And these are on the order of tens to hundreds of meters per second wide. So on the scale of an entire absorption line, they're typically not visible by eye. But what I want to talk about more is the dance of granulation on the time scale of minutes. So I can't tell if this is animating. It is, that's great. And so if we look at a bisector in disk resolved light. So if we look at an iron line, for example, this is the iron 15434 line, and we observe this line in a time series. So here we're looking at 15-second snapshots and measure that bisector. We can see it's dancing left to right. And that dance left to right is largely the pulsational mode of the sun. So the pulsations are moving our whole line left and right, and those are largely radial. But if you by eye sort of correct for those, you can see that this bisector is also changing shape. You see changes in curvature, especially in the upper lower regions of that bisector, and those are tied to changes in our granulation that's happening stochastically on timescales of minutes and seconds. So over the course of observations that we're taking for the sun or for other stars. And of course, the shape of our bisector and its little dance varies with limb position. If we look more towards the limb, we're sampling different heights in the solar atmosphere, different velocity fields. We get a different shaped bisector. So instead of that C shape towards the limb, we get a slant shaped bisector. And you can also see it's not dancing as much due to that pulsational mode. And that's because these are mostly radial. And when we look towards the limb, we are sampling less of that mode that's moving back and forth. And because of this complex dance, I want to emphasize that the mitigation strategies that we have developed for other sources of stellar variability aren't going to work for granulation. So we've seen that the sort of go-to strategy for binning down our residual amplitude for P modes is to just integrate for longer than the principal P mode of your star. So the idea is if for the sun, we have like a 5 or so minute P mode, that's the peak, just integrate for longer or take multiple observations and bin them together. And that can get us down to a residual amplitude from P modes of 10 centimeters per second or lower. Simulations from Nadège Mounier of granulation and supergranulation like we have in the sun show that if you were to try to brute force bin down your granulation residual amplitude, it would take you all night. You would need to observe optimistically your star for the entire night, multiple hours to get to 13 centimeters per second. And so if we want to be probing the sub 10 centimeter per second level, we need to develop strategies for understanding and mitigating granulation that are novel and new. And that's just to emphasize this point. And so we have seen through this conference and in recent years that people have been developing strategies for telling shift changes that measure the motion of the center of mass of your star due to a Doppler reflex from a planet and separate those from line shape changes that are induced by activity, or in this case, I'm talking about granulation. And so my contribution to this is that I have been using solar data to produce spectra, time series of spectra specifically, where the only thing changing from observation to observation is a change in line shape driven by stochastic variations in granulation. And so using this solar data, we sort of have the ground truth. And if we have the ground truth, the hope is we can better test and develop these methods for separating shift changes from shape changes. And so we wrote a code to do it. The contrived acronym is GRASS, the Granulation and Spectrum Simulator. And first, I'll describe the output. So basically what GRASS gives us is a time series of spectra. And as I said before, the only thing changing from observation to observation is that line shape change due to variations in granulation, the dances of those granules. And the way we do this is we take disk resolved observations of the sun. So rather than doing this from MHD simulations, we let nature do physics for us. And so we have these observations from the LARS spectrograph that were originally published in Lunar Butcher et al. 2018 and 2019 that are time series of spectra at 41 positions on the solar disk observed at R of 700,000 for tens of minute time sequences for about 24 solar lines. And these are our input. And those 24 or so solar lines probe a variety of wavelengths. So we span a good chunk of the optical, but they also have different excitation potentials and Landé G factors. And as we've seen in previous talks, lines with different parameters are probing different layers in the solar atmosphere and produce or probe different velocity fields, produce different noise signatures or signals, depending on how you look at it. And so more on this input data, essentially what we do is we take these spectra, these time series of spectra at each position, we find the lines in those spectra, we measure a time series of bisectors from each of those lines, and then we also measure the line's width as a function of depth in the line. And these two pieces of data, the bisector and the width as a function of depth, give us all the information we need to uniquely specify a line shape at any given instance at time. And so once we've measured those, what we then do is tile a stellar grid and go ahead and inject those time series of bisectors and width functions into each tile of our grid. The grid is artificially sparse here for presentation, but the idea is we just take the radial position on our grid, find the nearest data that we took, and inject that. We also apply a random phase offset to each movie, and so these bisectors and adjacent cells, even if they're drawn from the same observation, are not dancing in sync. And this produces the effect of spatially binning over our P modes. We can also tune our limb darkening and differential rotation, our inclination, et cetera, to model other sorts of situations like that might arise with different stars. And then once we have all of these bisectors injected, we go ahead and sum over the disk. And what we get out is a spectrum as a function of time. Again, only thing that's changing is our line shape from granulation. Comparing our synthetic disk integrated line shapes, in this case, the IRM 15434 line, to direct observations of the disk integrated line shape, in this case, the IAG Solar Atlas, we can see we do quite well. So this model, which takes in disk resolved observations, produces pretty accurate disk integrated observations. And this is especially true when we fit out shallow line blends in the wings of this line. If we measure a bisector and zoom in on that x-axis, we can again see that we reproduce disk integrated bisector shapes really well. And so we can take these disk resolved data and produce great disk integrated data while preserving that time step. Currently in prep, I am writing this up and making these plots, comparing all these lines for these other solar lines. So look for this work coming soon. Something else we also do to model the other lines is there's this idea that to first order, the bisectors of shallow lines should resemble the upper portions of the bisectors of deep lines. And that's just because in our toy model of line formation, the wings of deep lines are forming at similar physical depths in the solar atmosphere as the cores of shallow lines. And so what we do is we take our deep lines and we just chop the bisectors that we inject different depths in order to model shallower lines. And so if we do that and we produce a time series of lines from these different bisectors, chopping to different depths, we can look at the RMS we see in velocity as a function of our line depth. And for this iron line specifically, we can see that as we go to deeper line depths, we see greater apparent variability. But a point I want to drive home is that the story is not the same for different lines. If we look at different lines chopping to different depths, we can see that we have different offsets on our y-axis, and some of them are differentially sensitive to that chopping depth. So our lines, again, are probing different velocity fields in our atmosphere, telling us different things. And again, of course, I have all of this in prep currently, so look for that work coming eventually. And using these lines and chopping them to different depths, something I've done is produced a large library of time series of spectra in the optical. If these are something you're interested in working with for developing methods, when I publish this paper, I will be uploading them to Zenodo for you to play with. But in the meantime, if you want something preliminary to play with, talk to me. I'm willing to give you some data. And eventually, if you're not happy with what I'm giving you, you can also produce your own. We have a GPU implementation of this code that will let you synthesize full spectral time series if you have a GPU on order of seconds. And so you can do what you want. It's your playground. And the last point I want to make before I conclude is that spectral resolution matters. And this is something I've been looking into with this code. And so here, what I have is my model disk integrated bisector for an IRM1 line. And I have it at a couple of different spectral resolutions, the fiducial one being the R of 700,000 native resolution of the input observations. And you can see as we go to lower resolution, in addition to these massive wiggles that we get, our bisector also just becomes more vertical. Those wiggles are, of course, because our line profile is undersampled. And so when we go to measure a bisector and do our interpolation, we get lots of interpolation noise. But if we go ahead and measure something like a bisector inverse slope for this line and correlate it against the apparent RV of a line in a time series, so I've taken some data, produced a time series of spectral lines, measured the radial velocity of those lines, and also measured their bisector inverse slope. You can see that we have a correlation between bisector inverse slope and delta RV. And what this is telling us is that this line is containing information about the apparent RV shifts that we see from granular variability. And this is great because it means that if we see a change in the bisector of inverse slope, that's telling us something about our change in line shape and a fake RV that's activity driven or variability driven rather than being driven by a motion of the center of mass of the star. But if we go ahead and do the same thing for lower resolutions, you can see that as I lower that resolution, that correlation between bisector inverse slope and delta RV weakens and eventually becomes flat, disappears. And so at lower spectral resolution, we lose that ability to correlate our bisector inverse slope, our bisector information, with the apparent delta RV of our line. And here they are, all are together, if you can actually see past that rainbow mess. But the gist is, at lower spectral resolution, we're throwing away, or rather not collecting information that is vital for disentangling variability in the line from true RV shifts. And with that, I will put up my summary slide and I'll take questions.
Okay, we've got a question back here.
So the solar 5-minute oscillation, there'll be a phase relation between velocity and intensity. When that's averaged over time, does that affect the bisector, or is the bisector completely determined by granulation?
I didn't entirely hear the question because of the speakers, but you're asking about how oscillations can affect bisector shape?
Yeah, because in the oscillation, phase and velocity can be correlated.
Yes. Yeah, so oscillations can also impact your bisector shape, but I have not gone through and precisely quantified in those bisector animations, for example, what is attributable to granulation and what is attributable to oscillations changing that bisector shape. That's something I'm interested in looking into, but I would need to consult the expertise of others to figure out.
That would be an interesting exercise. Thank you.
All right, we're out of time, so I'm going to have Marina